Why the discovery of dark oxygen gives us a new solution to the Fermi Paradox. Some of the wildest things humanity has ever stumbled upon were found in the depths of space and the mysterious bottom of the ocean. Recently, while diving 13,000 feet down in the Pacific Ocean, dark oxygen was mysteriously discovered in the terrifying darkness. And no, dark oxygen isn't the opposite of oxygen like dark matter. It's just a source of oxygen that shouldn't be there. Since the hunt for alien biospheres has mostly been about searching for oxygen deposits, this discovery might just help answer one of science's biggest questions. How does this accidental find give us a new angle on the Fermi Paradox? Let's find out. A big challenge moving forward in the search for alien life, especially now that we have the James Webb, is figuring out which gases really signal a biosphere. The tricky part is that a lot of gases life on Earth produces aren't just from living things. Methane and sulfur dioxide, for example, can also come from geological processes, so they don't cut it as biosignatures. Sure, sulfur dioxide can be made by biology, but in many places in the solar system, you'll find it from non-living sources. So it really can't stand alone as proof of life. Volcanoes make it, industries pump it out, and even chemical reactions can create it. It's all around. That's the big issue. Biology, volcanoes, and chemical reactions all churn out similar gases. The key is to pinpoint the gases that biology produces that nature doesn't, and then look for another gas that seems out of place and go from there. Stay with us as we explore the recently discovered source of oxygen and what it means for the Fermi Paradox. But to begin, let's first establish some important context. To tackle the Fermi Paradox, scientists are focusing on gases produced by living organisms. And as we mentioned earlier, the trick to finding out which gases come from biological processes in our solar system is to look for those that are less common in nature. Then we should check if there's another independent gas that seems a bit out of place. We want to focus on gases that are in some unexpected amounts, suggesting some kind of imbalance in their environment. Usually these gases need a way to be replenished, which seems unlikely without some outside help, like life. A great example of this is oxygen. Earth is rich in oxygen, largely produced by plants. However, it's long been suspected that atmospheric oxygen alone isn't a reliable biosignature without accompanying independent gas disequilibrium. While oxygen is reactive and must be replenished, we still don't fully understand all the processes that contribute to its presence, and a new mechanism has recently emerged. This development holds significant implications for the search for extraterrestrial life. Moreover, when we examine regions of the universe such as nebulae, we find substantial amounts of oxygen that aren't biologically produced. The universe easily generates this relatively light element. It's when we encounter a combination of gases that are not typically formed without biological processes that we can begin to consider the possibility of life in an exoplanet's atmosphere. It's also important to remember that life exists not only on land and in the air, but also in the ocean. We're entering an exciting phase where we can now begin to study exoplanet atmospheres, though we're still in the early days. Now, let's look at the shocking discovery that was made in the depths of the ocean. What's this mysterious discovery? Can science explain it? In 2013, Andrew Sweetman, a researcher from the Scottish Association for Marine Science, stumbled upon something unusual on the ocean floor. He was looking at a very large marine ecosystem between Hawaii and Mexico called the Clarion-Clipperton Zone, which is larger than India. As part of his research, Sweetman's team sent down machines to gauge oxygen levels in this area. These automated landers sealed off sections of the seabed with cylinders about 22 centimeters squared and monitored how the oxygen concentrations in the seawater shifted over several days. From their earlier studies, Sweetman and his team expected to see a steady decrease in oxygen levels as marine organisms consumed it. The rate of consumption could provide insights into the quantity and health of marine microorganisms, reflecting the overall state of the seabed. However, during this particular mission, something unexpected occurred that Sweetman had never seen before. Instead of the oxygen levels dropping, the instruments indicated that the enclosed water was actually gaining oxygen over time. Something was producing oxygen instead of using it up. This surprising discovery, now referred to as dark oxygen, was announced recently, prompting questions about what was really happening and why it was named that way. These findings are quite intriguing, so let's explore how oxygen usually behaves in the deep sea and how it relates to the Fermi Paradox. Back to the discovery. So Andrew Sweetman and his colleagues published a paper titled Evidence of Dark Oxygen Production at the Abyssal Seafloor, where they describe a surprising new oxygen they discovered. At over 12,000 feet beneath the ocean's surface, sunlight doesn't reach there. This means that photosynthesis is off the table. So finding oxygen down there was unexpected. The Clarion-Clipperton Zone, where this discovery was made, is fascinating for several reasons. It actually hosts a diverse array of life, much of which remained unknown until 2016, with many more species still waiting to be discovered and cataloged. Initially, the findings were met with skepticism, and the team spent a long time verifying their sensors before accepting that the readings were accurate. In 2021, they returned to the area for a different purpose, to survey the seabed for mining opportunities, as the region contains valuable nodules rich in industrial metals. Once again, they detected significant increases in oxygen as they descended deeper. They investigated to see if some form of life was responsible, but it quickly became clear that while life was using oxygen, it wasn't producing it. For context, the second exploration was in search of polymetallic or manganese nodules, which usually start as little seeds, like a shark's tooth or a shell shard. Over time, valuable metals like manganese and cobalt build up around that seed, forming a structure that's kind of like a pearl, though not as visually appealing. Before we continue, make sure to hit the subscribe button and click the notification bell to stay updated with our future videos. Now, how exactly was this dark oxygen formed? At first, it was unclear how the chemistry of these nodules could be responsible for producing the oxygen, but they seemed the likely culprit somehow. Initially, the idea of radioactive decay splitting water molecules was considered, but that wasn't the case. It also wasn't due to oxygen-containing minerals decaying and releasing it. As it turns out, there's a known effect with these manganese nodules that sometimes have them referred to as batteries in rocks. If you take a regular AA battery and put it in salt water, it will bubble and produce hydrogen and oxygen because the electricity splits the water molecules through electrolysis. It appears the nodules can do this too, especially when clustered together, acting like little underwater batteries. Interestingly, this dynamic has some potential implications when it comes to abiogenesis, or at least the aftermath. The prevailing view has been that complex life evolved only after photosynthesis emerged with the rise of cyanobacteria and the resulting oxygenation of the environment. However, this dark oxygen discovery suggests there may have been alternative pathways for oxygen production that could have influenced the early evolution of life on Earth. This dark oxygen discovery has recently opened up a new mystery to explore. But how does it provide a new insight to the search for life beyond Earth? Since the formation of these nodules is a geological process, biology isn't necessary for it to occur. All you need is some kind of seed, like a pebble, and the right dissolved metals in the water, which most of the solar system likely has. This means that nodule formation could be happening in the oceans of moons like Europa and Enceladus, as long as those oceans are in direct contact with the rocky ocean floor and not insulated by a layer of ice. If that's the case, moons like Europa could have a way of oxygenating their oceans. It's typically assumed that any potential life on Europa or Enceladus would be microbial and anaerobic, making complex life seem unlikely without oxygen from photosynthesis. But if we can have deep ocean oxygen generated by the right geology instead, then the possibility of complex life existing in these oceanic ice shell moons becomes more plausible. This opens up some intriguing possibilities. First, there might be an unknown ecosystem under Europa's ice, a macrofauna that includes various aquatic species, potentially resembling fish, jellyfish, octopuses, and even alien analogs to space sharks. Bioluminescence? We have no way of knowing, and the potential is vast given the number of ice shell moons and smaller bodies in the solar system. Titan, Oberon, Ganymede, Callisto, Pluto, and countless Kuiper Belt objects could all be hosting oxygenated oceans beneath their icy surfaces, possibly supporting more than just microbial life, just like Earth does. But it goes even further. Ice shell moons are likely common throughout the universe. If we have so many in our solar system, they could be everywhere, vastly outnumbering larger planets like Earth. What are the implications of this? It's quite chilling to think about. There doesn't seem to be a limit to this possibility. Could intelligence arise in such environments? With sufficient oxygen, it certainly could. Now, could that intelligence ever leave its icy shell and venture into space? That's harder to determine. It's possible that such beings might not even be aware that space exists. All they would see is an ice wall above them, trapped in an ocean where creating technology would be a significant challenge. Even smelting metals would be difficult. Plus, the very metals they rely on for oxygen production could be what they're mining. If they over-extract, they risk extinction. This line of thought leads us to a new perspective on the Fermi Paradox. If we were to take this a bit further, it appears that complex civilizations arising in ice shell environments are faced with a daunting dilemma. If they fail to manage their resources responsibly, they risk suffocating themselves, a fate far worse than the consequences of fossil fuel use. On the other hand, if they choose to live within their means, they may never develop the capability to escape their icy confinement. One potential advantage of ice shell moons and planets is that they're less affected by the type of star they orbit. For instance, a red dwarf star shouldn't pose a problem, as the ice would protect the ocean beneath. However, the prospects for surface habitability around red dwarfs are looking grim. The violent nature of these stars and the lack of atmospheres on the planets around TRAPPIST-1, or red dwarf, are casting doubt on the existence of Earth-like planets. This leaves us with Type G and K stars as the most promising candidates for supporting life. As a result, the pool of potential surface habitable worlds is shrinking, and it's possible that such planets are the exception rather than the rule. If civilizations can't survive in aquatic environments, it's no wonder we haven't detected any signs of life. We're simply too far from other planets like ours, and the life we're close to is either trapped or may have self-destructed once it reached the point of manganese nodule mining. This newfound insight from the recent discovery is fascinating, as it could give us a clue to where an unknown life form might be. What do you think about this theory? Do you think this proves a clue to extraterrestrial life forms? Feel free to leave your answers in the comments below. If you liked the video, then you should check out the one on your screen. This video on 8 most possible solutions to the Fermi Paradox will blow your mind. Thanks for watching.